About 5 years ago, we asked ourselves an important question, and that was, if we could start with an absolute clean sheet of paper, what would be the best topology to design a propulsion system for a UAS, unmanned aerial systems aircraft, that was high endurance, required good stability for optics for ISR applications, and was just a very high quality piece of equipment. And we quickly came to the conclusion that the current systems that were on the market, mostly Boxer twins, were not the right solution. The Boxer twin historically was the right solution for hobby aircraft. It allowed air-cooled cylinders to stick out into the airstream and cool properly. It packaged decently, had decent power, was inexpensive, but it really did not fit the needs of a high-end, high-endurance, high ISR application aircraft. So immediately, we took our experience from the auto industry and power sports and looked at different topologies, and very quickly we came to the conclusion that a straight triple, 3 cylinders in alignment with each other, was the best solution. And the more we thought about it, the more we did the background math, the more we did our early CAA work, we realized, wow, this is really a lot better than all the prevailing solutions that were out there. And there's a whole bunch of reasons why that's the case. We'll go over each one of those in this video. And just quickly to start out, it balances really well. Primary and secondary shaking forces are inherently balanced. And maybe more important is that the torque fluctuations during a single cycle of each crankshaft rotation are really low compared to a Boxer twin. A Boxer twin is essentially a big single, and the straight triple, the cylinders fire every 120 degrees of crankshaft rotation. And so what that means is that you're essentially reducing the amount of input forces into the fuselage by 80%, and the amount of twisting and torquing that goes on in the engine bay is perturbating the optics that much less. It's just that much better of a system. And then as we started designing further, we realized there are many, many other advantages as well, including power. Unlike a Boxer twin, you can use the intake and exhaust system to tune the engine for higher performance. You can use the exhaust system to tune the engine for better fuel efficiency. It's much quieter because you've got 3 combustion events per cycle that a relatively small and lightweight exhaust system can handle, versus 1 big combustion system per cycle with a Boxer twin. And there's a fair amount of other advantages too that really come into play when we talk about heavy fuel. One of the most important features of a straight triple, and it's very evident when you actually see the engine, and it's even more evident when you see the engine installed in an aircraft, is its ability to create a very aerodynamic platform. As I mentioned, the Boxer twin has its purpose. You have to have cylinders that stick out in the airstream for good cooling. With our application, this is liquid cooled, and you can only imagine, a fuselage conforming around the engine, and very small amount of air relative to an air-cooled cylinder is required to flow over a radiator. Much more surface area in the radiator. The temperature rise over the radiator is greater than it is over the fin of the cylinder, so the amount of air that you need to scoop in and bring around the engine is a lot less. The bottom line is the overall aerodynamic package can be up to 20% slipperier than a typical air-cooled Boxer twin application. So I mentioned liquid cooling as being a way to reduce airframe drag, and it is. There are other things that liquid cooling does for us as well. Maybe the most obvious one is that you can maintain very, very tight temperature control of the engine in even the hottest or coldest conditions. And what that does for you is a couple of things. One is you can keep the engine consistently below coking temperatures for carbon deposits. So the combustion chamber stays clean, the exhaust system stays clean, and the time between overhauls, which often is driven by deposits, is much, much longer. So big advantage there. The other big advantage of liquid cooling is the fact that the engine is much, much more durable. So things like seals and O-rings, cylinder walls, metals like the piston, keeping those in a very tight temperature range means that this aircraft can stay in service a lot longer without the need for an engine overhaul. One of the key features of the A99H, and the fact that we did take a clean sheet approach on this, was that we designed the engine from day one to be a good performer on heavy fuels. And what does that mean? There's really three big issues with heavy fuel. One is that you've got a very low volatility fuel that vaporizes poorly. It's difficult to cold start. It's difficult to run in colder conditions and in light load conditions. The other thing that heavy fuel is known for is building up a lot of deposits, and you've got to keep the engine in a very tight, narrow temperature range in order not to do that. Finally, there's the issue of detonation and the fact that your detonation limits are very narrow. Pre-ignition, or detonation as it's called, can do a lot of damage to the engine. So you've got to design the engine in such a way to stay away from those detonation limits. So what does that mean in terms of mechanical design? A couple of things. One is that we already had an advantage right from the start in that we were going from 1 or maybe 2 cylinders to 3 cylinders. And what that does is reduce the bore size. It allows the flame front to travel across the combustion chamber quickly and not allow those end gases to bake and pre-ignite. So that's one big advantage of going to a smaller bore 3-cylinder engine versus a boxer twin style engine. Secondly, temperature control. We've already talked about liquid cooling and how we can keep the engine in a very tight window. And it's amazing. The amount of deposit buildup in the combustion chamber and in the exhaust is virtually non-existent. And what that'll allow the engine to do is run over much longer periods of time without the need of an overhaul. Let's do a quick overview all the way from the firewall to the spinner cone of this engine, and some of the unique features and benefits that this A99H has, and how that can make your aircraft a better performing aircraft. Starting at the firewall, first of all, there is a additively manufactured super lightweight mount. It's a focal mount that allows the engine, basically, it allows us to separate two different key modes of input forces into the fuselage. One is the torsional mode, where we want to be very soft, and the other is the mechanical vibration mode, the primary and secondary vibration forces that we also want to mitigate, but we don't want the prop to be bouncing around as you're flying along. So we've got a very soft mode torsionally, and a little bit stiffer mode with typical vibrations, and the focal mount does a great job of mitigating all those forces going into the fuselage. A few other things you can see down in here. This is our belt drive for our onboard water pump. We've got dual redundant sensors. We call this our ACK pack, or our accessory pack. So it has the mount, it has the rear seal. It's got dual redundant crankshaft sensors, so that if one fails, and that's a key single point failure mode, that we've got another one for backup. And then also housed in this area is what we call our swirl tank. And most importantly, the swirl tank has a proportional valve on it, so that all of the coolant that goes through the swirl tank, it deaerates for one, but we control temperature really with a smart thermostat, and that's what this proportional valve on the other side is. It allows a variable proportion of the coolant to go directly back through the engine after it comes out of the engine, or it goes through the radiator. So you can have up to 100% of the coolant going through the radiator loop, or in very cold applications, or where the engine is starting up, you have 100% of the coolant going directly back through the engine itself. And that allows us, again, to have very, very tight temperature control, not just of the top end of the engine, but also of the cases as well. And that's important for running heavy fuels. All right, moving forward. As I mentioned, we've got liquid-cooled engine cases. Each case is separated so that we have air-fuel ratio control over each cylinder separately. We have a full-size plug. It's a fine wire plug, which allows essentially much longer durability and reliability of the plug, of the ignition system, so that you can essentially not worry about swapping plugs out in the field any longer. Our titanium exhaust system is a 3-into-1 system that allows what's called cross-stuffing, and what that does is it offers higher performance. It allows you to tune the exhaust, and it also allows us to recover some of the what's called short-circuited raw fuel that happens to go into the exhaust. It allows us to push that back into the cylinder for much higher efficiency. We've got a very flexible design on the front of the engine, so in this case, we happen to have a 600-watt peak starter generator, so the engine starts on this as well. However, this front generator mount is very flexible. We can run a series hybrid where all of the power of the engine goes directly into generating electrical power, or you can have different size generators that will not only start, not only generate, but they will augment using Power for Flight's IntelliGen system, augment shaft power as a parallel hybrid system. So for certain applications where you need a burst of power, whether that's a sprint or a climb, as long as you have enough battery power on board, you can use that temporarily to augment the shaft power and go faster and harder wherever that need may be. Finally, focusing underneath on the liquid to air radiator that you can see here. This is one possible packaging solution. In this case, this was designed around a pusher solution. So air intake scoops were on the side underneath the wings, high pressure part of the aircraft fuselage, and air comes underneath through the radiator, and then it also goes up and through the generator for cooling the generator on the way out. It's a very slippery installation, but that's not the only place that the radiator can go. Depending on the topology of your aircraft, whether you have a pusher or a tractor configuration, we can mount the radiator pretty much anywhere. Okay, intake side of the engine, a couple things to notice over here. One is that we've made a lot of provisions for just good harnessing. So for example, if you look at the phase leads coming off the generator, they tuck nicely in up under the intake manifold. They actually fasten to the bottom of the intake manifold. Things like cylinder head temperature sensors, plug wires up here, ignition leads here, the fuel rail, the fuel input here. Everything flows nicely back to the firewall and bundles very neatly and tidily. On this side of the engine, you can also see the log manifold, intake manifold. We have the fuel injectors that are actually case injected. So the injectors are not in the intake manifold. They go directly into the crankcase. And again, that's one of those things that we did to optimize for transient response on heavy fuel. And then here is your intake filter. What typically is done here is that a slippery, thick foam seal is placed between this intake port and the side of the fuselage, which wraps here, so the engine can move relative to the outer skin, the cowl, and then outside of that will be some sort of scoop or louver to pull air into the engine. So really nice air intake system. You're not going to get dust. You're not going to get rain in the system. It's very well controlled. The other thing is that, by additively manufacturing things like the intake manifold, we're able to incorporate lots of nice little features like the wire harness tie downs that I mentioned, and other things where we were able to combine lots of different parts into a single part for weight reduction and package improvements. Before we spent the 5 years designing and developing this platform, we spent a lot of time listening to our customers, both our military customers and commercial customers, and what their needs in a really good, high performance, high endurance UAS platform might be for propulsion. And we heard a lot of things. We heard that it had to be very reliable. We wanted it to be quiet, good aerodynamics, good performance, low vibration signature into the fuselage, heavy fuel capability, high durability. All those things the customers have said over and over that those were their key metrics that they were looking for in a propulsion platform. And quite often, there's a lot of trade-offs between those, trade-off between noise and performance, for example. And we've been able to, with this platform, minimize the trade-offs and optimize a lot of those key metrics that can't be optimized with other topologies. So for more information, go to CobraAero.com, give us a call. We're here, and we're excited to have this engine ready for you in your aircraft.